All right, welcome back everyone. Today we're going to be looking at a difficult topic, the loci of a complex number. So definitely this is near the harder end of the topic. In NCA, these questions are usually excellent, sometimes merit. And it definitely does put a lot of people off. I guess the word loci in and of itself puts people off. They don't know what it means. It kind of seems like this foreign thing. We're going to try break it down, make it a bit simpler, and go through some examples of how to find the loci of a complex number. First of all, let's just try and understand what the heck it actually means. So it's not that tricky. I've managed to kind of simplify it down to one little sentence. So it is the set of numbers that satisfy a rule. So the set of numbers is like a group of numbers in a kind of pattern or some sort of, there's something that links them together. And the thing that links these numbers together is there's some rule. Now, we'll give some examples of how this works. Usually, in the context of this topic, it boils down to being numbers that lie on a line with each other or numbers that are on a circle with each other. But before we do that, let's just look at some easy ideas to get an idea of how there could be a rule that might link some numbers together. So we'll do three kind of basic examples, hopefully, that kind of show us how we could get a rule with complex numbers. And how we could describe the locus. So, first one, describe the locus of complex numbers given by, and they've told us that little REZ, that just means the real part of Z. Remember, we're using Z to represent a random complex number. We want to describe the locus of complex numbers given by the real of Z equaling to 2. So, the real part of a complex number equaling 2. So, let's just do a few examples. My Z could be 2 plus 3i. My complex number could be Z is equal to 2 minus I. We could have Z equals to 2. That's 1 as well. So it's all complex numbers that have 2 in it. Now we want to describe these with some rule or some pattern. So usually we want to try and see what they look like. So if I was going to plot these complex numbers onto my complex plane, they all have the real part equaling to 2. If I plot my 3, I've got 2 plus 3i. So that's up here somewhere, 2 plus 3i. I have got 2 minus I. That's down here somewhere. I've got just 2, which is right here. So it turns out it's all complex numbers that are sitting on this line. And in fact, this is how we usually describe these locuses, is it's to do with a line or a circle usually. So how do we describe this line? Well, in general, when we talk about a complex number Z equaling x plus iy and how we relate that to our x and y graph, this is my x coordinate, my x-axis is my y-axis. If we were trying to write a vertical line, you've got to remember all the way back to year 11. This is simply, my answer is y is equal to, sorry, I take that back. What am I talking about? X is equal to 2. And it's a line. It's the line x equals 2. And it's clear, you can see x plus iy, all of my x's were 2, but this is the actual way that we'd write it. Seems too simple, too easy. Let's look at another one. Describe the locus of complex numbers with the distance to the origin of 3. So all complex numbers that have a distance to the origin, remember our origin is right here in the middle, a distance of 3. So we can take the three extreme ones, 3 here in my real, 3 in my imaginary, negative 3 over here, and negative 3i. So they all have a distance to the origin of 3. But if you've kind of tackled any question similar to this before, you realize that there's a whole lot of points. Like if I make a distance here that's 3, it actually becomes all the points on this circle. Not bad, a little bit wonky, where the radius is 3. So this distance here is 3. For all of them. This length over here, 3. This length over here, 3. And we're going to look a little bit about how we'd write a circle, but this particular circle would be x squared plus y squared is equal to 3 squared, which is 9. This is the equation of a circle. If you have never learnt about the equation of a circle, for example, your class has never done conic sections, you've never looked into circles, it may be a good idea before you tackle this loci subject just to get a rough understanding of what a circle's equation is and how it relates to the graph. You will need a little understanding of that. Nothing major, but you will need to know how the radius is over here and so on. And last example, describe the locus of complex numbers given by the arg of z. Arg of z means the argument of z, or the angle that z makes with the real axis. If you haven't looked at the video about that, I highly recommend you do. Equaling to 45. So again, let's try to visualize what this might look like. The argument is equal to 45 degrees. The angle that we're making with the positive real axis is 45 degrees. So all the complex numbers that satisfy this rule that sit on this line, so all the complex numbers that satisfy that rule sit on this circle. All the complex numbers that satisfy this rule sit on that line. What about all the complex numbers here? It looks like it's another line. All the complex numbers on this line here. Now this is actually quite an easy line to write. The y-intercept here is 0, and the gradient is actually 1. It goes across 1, up 1, across 2, up 2, across 3, up 3. To make that 45-degree angle, it cuts my 90-degree perfectly in half. It has the across 1, up 1 on it right here. Across 2, up 2. The gradient is 1. The y-intercept, or the c, is 0. And so my line is y is equal to x, 1x plus 0. That's my rule. Now there's one extra bit that makes this a tiny bit harder, is that the line y equals x technically keeps going down here. And we don't want these points down here, because these points down here do not have an angle of 45 degrees. They would have negative 135 coming down here. Remembering, if you've watched the modulus video, we want to go positive 45 up to here. I do not want to go negative 135 down to here. These do not sit there, but they are on the line y equals x. So I need a extra little restraint on my my description. Y equals x does not fully describe argument equals 45. This would satisfy argument equals 45 or argument equals to negative 135. So we simply just have to say, let's keep x in the positive region. As long as I keep my x value here, I don't want x to be negative 1. I don't want x to come anywhere down here. If I had negative 1, that would be down here. That's not what I want. As long as I keep my x in the positive region, x above here, and the y is the same as x. So for example, 1, 1, 2, 2, 3, 3, 4, 4. Any number on that line, 5, 5, 6, 6, 7, 7, 8, 8, 9.5, 9.5, 3.1, 3.1, whatever, they satisfy this argument being 45 degrees. All right. That's 3 easy examples. Now you probably won't get one, maybe this bottom one in an exam, but the top 2 probably not in an exam. So in an exam, or to really tackle this topic, you do want to have these 2 pieces of information. Let's just cover up my example real quick. Sorry. All right. So we want to know comfortably the equation of a line. Y equals mx plus c. In this, we know that m is the gradient and c is the y-intercept. Hopefully you are familiar with this. This is year 11, year 10 stuff right here, year 12 as well. Gradient m, c is the y-intercept. This is our equation of a line. The other thing you want to have down, like I said earlier, is the equation of a circle. X squared plus y squared equals r squared, as long as the center is right there at the origin. If it has shifted left or right, we have x minus p squared plus y minus q squared is equal to r squared, where pq would be my center and the radius would be r. That would be a circle that is not around the origin. This point here would be p and q, my center, p here, q here, and the radius would be r. And this would be the equation of that circle. So you'd want to have that roughly locked in before you approach some of these loci questions. With that intact, let's have a go at 3 examples to see how this can pop up. These are more exam style questions, probably tending towards merit. Some of them excellent. Let's have a look here. Describe the locus of z in the complex plane if z satisfies this thing. Now, before we approach this question, you must know what this modulus symbol is, and if you have not watched the video or learnt about the modulus, you will need to do that before. You cannot approach this question without knowing what these lines are. So if you do know what the lines are, they mean the distance to the origin, and they also, there's a formula for it, it's the real part squared plus the imaginary part squared, all square rooted, and we get that from Pythagoras. So we're going to let z equal x plus iy in this case. We're going to substitute it in, so it's the modulus of x plus iy plus 2y is equal to 4. They're really asking all the points that satisfy the condition that when I add 2i to the complex number and find the distance to the origin, it equals 4. What points satisfy that condition? It's hard for our brains to visualize exactly what's going on here, but really I'm thinking about a distance to the origin question where it's been moved a little bit. So in this case here, x is my real part, y and 2 are my imaginary part. So when I use the formula, it becomes x squared plus y plus 2 squared, all square rooted, is equal to 4. So this is my modulus formula, the real part squared plus the imaginary stuff squared, all square rooted. This is directly Pythagoras, is equal to 4. And now I can square both sides and have x squared plus y plus 2 squared is equal to 16. And at this point, people usually panic and think, oh, geez, I don't really get what I'm doing here. Am I expanding this? Where is this going? It turns out that this is actually the finish line. It's actually not too hard of a question. The only part now is to recognize that this is the equation of a circle. P in this case is 0 because there's no addition to the x. The Q in this case is going to be -2. And my R in this case is 4. So this has a center. It's a circle, I should say. A circle with center at 0, -2. And the radius 4. I've described it. This is the description. All the points on the circle. So we'll try to explain it a little bit. I'm not going to go too deep into it. Here's my circle. The center is 0 but down 2, so we're here. Radius is 4, so we're going up to 4 over here, across to 4 over here, across to 4 over here, down to -6 here. We draw our circle. It turns out if I pick any point on this circle, so you could pick an easy one, maybe up here, which is x equals 0, y is equal to 2. And then so any point on this is my z, any point here, and then when I plus 2i onto that, so this was already 2i, and then I add another 2i onto it, that will be 4i. The distance of 4i to the origin, which is this modulus sign, is 4. So these are my z's. This is my z numbers that satisfy the condition. Z plus 2i, distance to the origin is 4. So if I pick any number here, I could pick this one down here, which was -6i. And if I plus 2i onto it, so we'll say z is equal to -6i. That's something that satisfies this condition. Z is equal to -6i. It's down here. It's the bottom of my circle. That this was -2i. The radius was 4, so I'm coming down 4 here. If I take that complex number, z, put it in here, so I add 2i onto it, I get -4i. Take the distance to the origin of -4i, that distance is 4. And it turns out any point on this circle, if I add 2i onto it and find the distance to the origin, it will be 4. We've shown it algebraically, but this is actually the visualization of what is happening. Let's try another one. Describe the locus of z if z plus 5 modulus is equal to z minus 3 modulus. So I'm trying to find z's, complex numbers, like I did in that last one, that when I add 5 onto it and calculate the distance to the origin, it's the same as taking away 3i from it. Very hard to visualize or just roughly get this. We're going to go through similar to that last one with algebra. So we're going to, again, let z equal x plus iy. Put that in. We've got x plus iy plus 5 is equal to x plus iy minus 3i. Use our formula for the real part squared plus the, x plus 5 squared plus the imaginary squared, which is y, all square rooted, is equal to the real stuff squared. On this side, this is going to be just x, and the imaginary squared, which is going to be y minus 3 squared, all square rooted. Just putting them into the formulas. I can square both sides right from the get-go here. Get rid of my square root signs. All right, and again, this is the point where people panic. They get to here. You can kind of follow the motions getting to here, and then I don't know what to do. Now, the last one, when we got to here, it was already the equation of a circle. Right here at the get-go is the equation of a circle. Circle must be some form of x squared plus some form of y squared is equal to r squared. There's no kind of deviation from that. This is a deviation from it because I've got some sort of x squared, some sort of y squared, but then some sort of x squared and some sort of y squared. Once you've practiced a few of these, you kind of get the motion of it. In this case, I want to expand and simplify as much as possible. So I'm going to expand this out, and hopefully it boils down to another simple circle, or maybe it'll be a straight line. Let's have a look. Expanding this bracket, x squared plus 10x plus 25 plus y squared. Remember, expanding that bracket is not just x squared plus 25. You have to imagine two brackets, expanding it using your whole method. This is x squared. This will be similarly y squared minus 6y plus 9. That's imagining there was another bracket that said y minus 3 and opening that up. All right, so the beautiful thing is I can subtract x squared from both sides, and it's gone. Or move that one over and make it a minus, it's gone. Move this y squared over, it's going to cancel with that one. And I'm going to end up with, sorry, that was a y term here. I was wondering where the heck my y term went. It's going to end up as 10x. I'm going to minus this 9 over to this side. So this becomes plus 16 is equal to negative 6y. And now I'm going to divide both sides by negative 6. And end up with negative 10 over 6x minus 16 over 6, and that equals to y. Why did I do that? Well, now I have something that is y is equal to mx plus c. I've written it on the wrong side. I mean, I can move it over here. I can simplify that as well. Negative 5 over 3x. I can simplify this as well. Minus 8 over 3. Just halving all of that. And this now is a line. You're hoping that it either boils down to be a line or a circle. The hardest type of questions are an ellipse. We might save them for another video. And that's finished. So we can talk about this now. It asks us to describe it. So we've got down to here. How do I describe this? Well, first of all, it's a line. So a line. And what do we know about this line? What's the gradient of the line? The gradient, in our case, is negative 5 over 3, the m, the part that is with x, and the y-intercept is equal to negative 8 over 3. It's going to be an ugly line to draw. Luckily, it didn't want us to draw that. Let's have a real quick gaze at what it might look like. The y-intercept, negative 8 over 3, that's just under 2, so it's down here somewhere. And it's going down by 1.6, so it looks something like this. Probably drawn it too steep, but this is what my line roughly looks like. These are my z's. So this is my z that satisfies it. Now, if I pick any z on this line, any number, so the easiest one would be picking that negative 8 over 3 point, and I add 5 to it and find the modulus, that should be the same as taking away 3i from it and calculating the modulus. But any point on that line will satisfy that rule according to our algebra. Let's try one more example. It's been a long video, but it is a hard topic. Alrighty. Similar to one of the early examples I gave, just as a kind of easy one, this is probably an exam style question. Describe the locus of z if the argument of z is equal to negative pi over 4. Now, it's nice. Any argument question, real quick, any argument question, we can easily describe its locus as long as the argument is on this axis here. So maybe that would mean the argument is 0. If it's a 45-degree angle, we can easily do that. This will be y is equal to x. This would be x is greater than 0, y is equal to 0. We could do this line here, which would be 90 degrees. And that would be the opposite of that. Y is greater than 0, x is equal to 0. We could do this line here, which would be 135 degrees, and that would be y is equal to negative x. Essentially, we've got this line, we've got this line, we've got these lines. All of these lines are quite nice because the gradient is easy to describe. They're just basically y and x are the same because they're all cutting perfectly. This would be 135 degrees. This would be 45 degrees. This would be negative 45 degrees. And this one over here would be negative 135. Or you've got your 90, your 180, your 270. Sorry, that picture's getting confusing pretty quick. Anyway, all of these have a nice way to describe them. They're all just some version of y and x being the same number. Some of them, they have to be one positive, one negative, both negatives, and the y negative, the real positive. But all of these have quite an easy way to do it. Our particular one we're trying to do right here is negative 45, which is this angle here, negative pi over 4. And we want to describe these points here. So you can think of some points that are on this line. Let's say we go across 1, we would go down 1. So x equaling 1, y equaling negative 1. You could do the same, 2 down 2, x equaling 2, y equaling negative 2. So all of these are the x is some number and the y is the negative of them. So we could say that the y is equal to the negative x. This is true for all the ones I've just said. The x was 1, the y was equal to negative 1. So you pick an x, and this helps you find what the y is. Let's say x was 5, y would equal to negative 5. If x was 10, y would equal to negative 10. So this equation is true for all points on this line. However, what if I picked x to be negative 2? That would mean y would be positive 2, but that would be x being negative, y being positive 2 would be over here, and that is not on my line. So the one other constraint we need with this, because this is true, but I don't want numbers ending up here, and that's when I pick a negative x. So we have to say that x is greater than 0. So these things here, so it's the line, y is equal to negative x, but we have to have a condition where x has to be bigger than 0 because we don't want points ending up over here because they no longer have an angle of negative pi over 4. They have an angle of 3 pi over 4, or 135 degrees. So the answer to this question is the line, all points on the line, y is equal to negative x, but we do have the condition that x has got to be greater than 0. All right, we've tried to tackle some questions here to do with argument. Hopefully this was useful. Thanks for watching. Catch you later.